Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we're looking at integrating factors. Integrating factors are used to solve first order linear differential equations, which means equations of the following form. So we have a dy by dx term. Since this is a first order differential equation, it will just be a first derivative. Then plus some function, which I'm going to call p of x, multiplying y, and y is what we're trying to solve for. And this is equal to some other function of x, which I'm going to call q of x. Now, some equations may have a function of x here in front of the dy by dx term, but since p and q are just any general function of x, we can just divide through by whatever's here to get this form. So, how do we solve this? Well, before I dive into the integrating factor method, we're going to look at a slightly simpler case of this equation to help to motivate where the integrating factor actually comes from. And what we want to consider is what we call the homogeneous form of this equation. So we still have our first derivative and our function of x, p of x, multiplying y, but we're going to first consider solving this equal to 0. If I rewrite this equation ever so slightly as dy by dx is equal to minus p of x times y, then this might start to look vaguely familiar for some of you. Because this equation we can now solve using the method of separation of variables. Now, don't worry if you've never come across this before. This isn't the focus of this particular video, but basically what you want to do is try and get all of the y terms on the left-hand side of the equation and all of the x terms on the right-hand side, and then integrate. So what we can do is divide through by y to then get 1 over y, the integral dy is equal to, and then we sort of integrate both sides with respect to x, or you can think of it as taking the dx here and like multiplying up, though it does work, but there is a formal mathematical process involving limit taking to justify this, but we're just going to do it here. So this will be equal to the integral then of minus p of x dx. So now we have all of the y terms on the left-hand side of the equation, all of the x terms on the right-hand side. And now if I integrate the left, I'm going to get the natural log of y. So we'll get ln of y is equal to the integral of minus p of x dx. And we can't really integrate this function because we don't know the form of p of x. That would need to be given in our question. But we can now say what the answer is, because if I exponentiate both sides, and there would of course be a plus c, if I exponentiate both sides, I get y equals, so then I get e to the integral, and then multiply by e to a constant, so let's call that a, times e to the minus the integral of p of x dx. And this is the solution to our homogeneous equation up here. Of course, we still need to integrate our function p of x, which again will be given for a specific question, but fortunately, we can check our working using the Maple Calculator app. All you do is click the integral sign and then input our function p of x, and the app will do the integral for you to allow you to check your answer. And if you're struggling when doing the integral for yourself, then you can even click on the footprints icon and it will show you the steps involved to get to the solution. So now we know how to deal with the simple case. When q is 0, we have our solution given up here. What do we do for the more general case, the inhomogeneous first order linear differential equation? And for this, we need the integrating factor. So the integrating factor, which I'm going to label as I of x, is equal to e to the integral of p of x dx. So you'll notice it's very similar to the solution to the homogeneous case when q is naught. We just have a plus here instead of a minus, and we don't include the integration constant a. Our first step to find the solution is to take our integrating factor, I of x, and to multiply the entire equation by it. So, on the left, I've got e to the integral px dx multiplied by dy by dx plus p of x times e to the integral of p of x dx, all multiplied by y, is equal to q of x times e to the integral p of x dx. And at this stage, it's really important to remember to multiply the right-hand side also by the integrating factor. That's a very common mistake that I see students make when solving problems of this type. Now, at the moment, this looks quite messy, and you might be thinking, well, how has multiplying by this actually helped us? And what we really want to do here, or what we want to spot, is that the left-hand side of our equation is actually the derivative of a product. So we sort of want to reverse engineer the product rule. Now, because I know where we're heading with this, what we can consider is if I had to do the x derivative of y multiplied by e to the integral of px dx. Then if I were to compute this, I have to use the product rule because I have two terms. I have y, which is a function of x, and I have the exponential, which is also a function of x. Now, if I apply the product rule to this, I'm going to get dy by dx multiplied by the exponential, which is exactly what we've got as our first term here. And then the second term by the product rule is y multiplied by the derivative of e to the integral of p. So I have my y, which remains untouched by the derivative, and then if I differentiate e to the integral of p, then the chain rule says I bring down the derivative of the power. So the derivative of an integral is the function itself, so I get p of x times e to the integral of p. So the second term in the product rule will always look like this. So what I've actually got here on the left-hand side is the derivative d by dx of y multiplied by the integrating factor. And now for the right-hand side of the expression, we just have the same q of x times the e to the integral of px dx. But now, because we've written this left-hand side as a derivative, I can now just integrate both sides with respect to x. So I can say that y times e to the integral of px dx is equal to the integral of qx times e to the integral of px dx. This whole thing integrated with respect to x plus an integration constant c. And finally, if I multiply both sides by e to the minus integral of p, then I can say that y, my final solution, is now e to the minus the integral of px dx, all multiplied by the integral of qx times e to the integral of p plus c. If I now relabel this integration constant c, let's instead call it a, then what we've actually got here is e to the minus integral of p multiplied by some other integral, but then plus a times e to the minus integral of p. And hopefully you've spotted that's exactly what we had up here for our homogeneous solution. So as with most differential equations that you may have studied or will go on to study, the solution is formed of the inhomogeneous part, which is the product of these first two terms, and then the homogeneous solution, or complementary function, it's sometimes called, which comes from e to the minus the integral times our integration constant, which is what we found up here with our first investigation. So to summarize, for any first order linear differential equation of this form, dy by dx plus some function p of x times y equals another function q of x, our solution will always be given by this, where importantly we get there using our integrating factor I of x, which is e to the integral of p of x. Now this of course looks quite messy as a solution, and if you enjoy learning formulas, you could just learn this as the solution, and then given any first order linear differential equation, you just plug in p and q in the right places and you would have your general solution. But often in practice, it's best to actually work with the equation that you're given and to follow three steps. So the first step is to calculate the integrating factor I of x. The second step is to multiply the equation by the integrating factor, which allows us to rewrite it as the derivative of a product, as we've just seen. And then the third and final step is to actually integrate then both sides to get this solution. So let's go through an example just to make all of that clear. The example we're going to look at is dy by dx plus 6x squared times y is equal to 6x squared times e to the minus 2x cubed. So as I just mentioned, step one is to calculate our integrating factor I of x. So step one. I of x is equal to e to the integral of p of x. P of x is going to be this term here, this 6x squared. So integrating 6x squared dx. So that integrating, that goes up to x cubed, divide by the 3. So it'll be e to the 2x cubed. So that gives me e to the 2x cubed. And we don't worry about integration constants when calculating the integrating factor, because we'll account for those at the very end. Now step two, remember, is to multiply the whole equation by our integrating factor, e to the 2x cubed. And then it means we can always rewrite the left-hand side precisely by the way in which we constructed this. We know this will always be true. We can write the left-hand side as the derivative of y multiplied by the integrating factor. So here, step two tells us that the left-hand side, when we multiply through, will be d by dx of y multiplied by the integrating factor. And that's equal to the right-hand side multiplied by the integrating factor. And again, don't forget to do that. So e to the 2x cubed will cancel with the e to the minus 2x cubed, and I'll just get 6x squared. Now, at this point, it's always a good idea, even though we know this is true, just to double check if we do the product rule on this term, we get back to our equation up here with the integrating factor. So if I do d by dx of y e to the 2x cubed, I'll get dy by dx multiplied by the integrating factor. So that's going to be that term. And then if I ignore the y, which leaves it there, and then I differentiate e to the 2x cubed, so I'll bring down a 6x squared and then get the same exponential. So we'll get 6x squared times the integrating factor, and then this times the integrating factor gives me 6x squared. So again, this will always be true on the left-hand side precisely because of the way that we constructed the integrating factor. That's why it has this form, but it is a good sanity check just to make sure that everything we're doing has been done correctly. Now the third and final step is to actually integrate both sides and get the solution for y. So we integrate the left and we'll just get y e to the 2x cubed, and that's equal to the integral of 6x squared, which we actually did before. So that gives me 2x cubed plus my integration constant, which I'm going to call a, because that's what we called it up here. Now we just divide by the e to the 2x cubed term to get the final solution, y equals e to the minus 2x cubed multiplied by 2x cubed plus a. And this is our solution to the original differential equation. Now, if we compare this to our general solution, just to make sure it all makes sense, we've got e to the minus the integral of px. So here minus, we've got the 2x cubed, which is indeed the integral of 6x squared. Then we've got plus a at the end, which matches perfectly. And then this thing is e to the integral of p. Well, that's exactly my integrating factor, which I know is e to the 2x cubed in there, multiplied by the original right-hand side. So if I multiply 6x squared e to the minus 2x cubed, if I multiply that by e to the plus 2x cubed, the exponential terms vanish. I just get 6x squared. And then I have to integrate that, because it's the integral of q of x times the integrating factor. So then I have to integrate 6x squared, which does indeed give me 2x cubed, which is exactly what's in there. Now there is one final step that you might have to complete in some of these problems, and that is going to be to fix our integration constant a. So if we're also given some initial data with our differential equation, so let's say, for example, in this case, I'm going to say that y of 0 is equal to 2. So to fix a, we just plug in x equals 0, and we need to make it equal 2. So that tells me that 2 must be equal to e to the power of 0, which is 1. So I get a 1. Square bracket 2x cubed, x is 0, so that's 0, plus a. So simplifying all of that tells me that a is 2. And so my final solution, which satisfies the differential equation here, plus this piece of initial data, is y equals e to the minus 2x cubed, all multiplied by 2x cubed plus 2. So to summarize, when solving a first order linear differential equation using the method of integrating factors, there are 3 key steps that you always must follow. Step 1 is to calculate your integrating factor I of x, which will just be e to the integral of the function multiplying y in the original equation. Step 2 is to multiply the whole equation, including the right-hand side, by your integrating factor. And that means you'll always be able to write the left-hand side as the derivative of a product. And the two terms in that product, again, will always be y multiplied by your integrating factor. And then for step 3, we actually do the final integration. So integrate the left and the right with respect to x, and then you divide both sides through by the integrating factor to get an explicit form for y. You might also need to fix your integration constant, but that isn't always the case. For those of you that would like to practice the integrating factor technique a little further, I've created this interactive worksheet in Maple Learn, which you can access for free by clicking on the link in the video description. Have a go and let me know how you get on. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed this video, and I'll see you all very soon. Take care.